So after the discretization and meshing and the assembly process, we have the total potential energy of the body or of the system represented here. Okay, we now need to arrive at equations of equilibrium where we can discover or solve for the nodal displacements, then subsequently the strains and the stresses. So not all these Q's are known. So we now invoke the minimum potential energy, and of course the theorem states that of all the possible displacements that satisfy the boundary conditions of a structural system, those that corresponding to equilibrium configurations make the total potential energy a minimum value. Okay, so consequently what we can do is minimize this total potential energy with respect to Q and subject to the boundary conditions. Okay, so that's kind of the overarching idea we're doing here from a theoretical perspective. So boundary conditions are specified in terms of displacements, right? So we have the displacement at point 1 is equal to some value, let's call it A1, and so forth, all the way to Q at point R is equal to A sub R. The displacements along the degrees of freedom, and those are P1, P2, and all the way to PR, are specified to be equal to the A's. In other words, there are R number of supports in the structure, right? And each support node has a given specified displacement that we need to solve for. For example, let's consider that bar again. There's only one boundary condition in this problem. What is it? Well, we can see these hatched lines represent that it's fixed to this wall. So we know that Q1, node 1, is going to be equal to 0. Now, as we talk about boundary conditions here, what we're doing is going to be applicable to 2 and 3 dimensions. We're going to see this. So a lot of times we'll use the term degree of freedom because one node in 2D, we'll talk about this in more detail, but one node in 2D has 2 degrees of freedom. It can move in X and it can move in Y, right? So we typically use the terms degree of freedom here instead of node. It's easy in 1D because one node only has 1 degree of freedom. Okay, but that will be expanded in the future. Boundary conditions are really important. You know, the improper specification of boundary conditions can lead to errors in your solution. We're going to see with a couple of applications how sensitive the problem is to boundary conditions. And so this, I can't remember the app, but we actually do a crushing tube problem where you get to really see the effects of boundary conditions. So you have to be careful about that. The other thing to remember is that boundary conditions act to keep from rigid body moving, translation. So for example, say we're pulling on a part, okay, well, if you pull or there's some numerical instability, it might pull off and go through space, okay? And it's then moving almost as like a rigid body. And so boundary conditions help you. A lot of times in fine elements, you need to fix 1 or 2 nodes. You need to think about how you constrain the rigid body motion from translation or rotation in your problems. And what you notice is that if it doesn't do that, sometimes it's a hard problem to debug because you have this rigid body translation. Your tools like CEE and the visualization module don't actually show your X, Y, Z coordinates sometimes, so that you can't really see that translation, which makes it tricky, especially in the static case, but it has moved through space. And of course, a lot of times in those cases, it does not converge. And so it can be a hard problem to debug. So you always want to think about how you can constrain rigid body motion. There are 2 approaches for handling specified displacement boundary conditions, okay, where we apply displacement to a node to move it, or we just say it's fixed. The first is the elimination approach, and the second is the penalty approach. We're going to go over the elimination approach here and in this class because it's really the easiest and most straightforward. So let's talk about that. To illustrate the basic idea, we're going to consider that boundary condition Q1 is equal to A1. So we have one single boundary condition. The equilibrium equations are obtained by minimizing the total potential energy pi with respect to Q, subject to the boundary conditions, basically what I restated, but along with the more specific example. So for an n degree of freedom structure, we're going to have Q. So these are the 1, 2, all the way to n number of nodes, and the same way with F. The stiffness matrix is going to be of the form like this. So here it's a n by n. Soon it's going to be a degree of freedom by degree of freedom. But in the 1D it's n by n. It's a symmetric matrix. So we start at 1, 1, and we go all the way up to, this is the first row and n nodes. And then this is the nth node in one column. And it goes all the way to n by n. The total potential energy can be written in the expanded form, right? So if we took this equation, or is it all the way back here, like something like this, we took this equation now and we expanded it. All right, how do we do that? So this gets a little kind of messy here, but we're going to start to write this equation. So we'll take this first term, 1/2 q times k times q. So do that linear algebra. You're going to be left with, well, q1 times k11 times q1. Next term is going to be q1 k12 times q2. You can actually write this down on a piece of paper and actually, show this math. Okay, and that's going to go on and it's going to continue. Remember, in this case, we're actually going to have a scalar value at the end, right? And so this is all going to add up. Here our last term will be q1, and then it's going to be k1n and then qn, depending on what n is. We then move on to the second row. So this increments by 1, q2, and we're now in k2, and then this goes to 1, and this is going to continue to 2 on the second portion here, all the way to the n value. Okay, so you can see the trend here, and you can of course work that out to prove it to yourself, but this is how it looks if you expand it. And that's going to go all the way down to this value, right? So this 1 or 2 will eventually be n, and then we're going to have qn, knn, qn, all right? And then we have to do this second term. So we do that whole process all over again, starting with 1 all the way to n. But that's the total potential energy expanded. Now you remember what we said. We said that Q1 was equal to what? Q1 is equal to A sub 1, we said, right? So let's highlight all of those Q1s. These are all our Q1s that we have in here, and we can put in A sub 1 there. Okay, so we could substitute this into the expression. And there you can see I've replaced all of those Q's with the A's. And what you notice here is, what do we see? Can we find any Q1s? No. These are actually replaced with A's, and that is that's like a value. It's like, say it's 1 or 2, whatever it is. That's a known value, A sub 0. It's a boundary condition. Either we specify, we do specify, either it's 0 or it's an applied displacement. And so what we've done here is we've eliminated, the displacement Q1 has been eliminated in the potential energy expression. It's been totally eliminated. So now we go back to our idea of this minimization, right? We want to minimize that energy. So, because if you remember what we said here, let's go back. It said the equilibrium equations are obtained by minimizing pi with respect to Q subject to the boundary condition. Okay, so now we need to minimize this with respect to Q. So here you can see we're going to minimize pi with respect to dq sub I, and we're going to set that equal to 0. That allows us to minimize it. So we're going to take our total potential energy here. Q1 has been eliminated. We're going to take our minimization equation. Note that this now starts at 2. We've totally eliminated Q1 out of this, right? And so we just start at 2 through n. So let's apply this first derivative, d pi dq2. d pi dq2, which are going to take all these terms and take the derivative with respect to q2. So applying that equation, let's look at this. This first term is 0, so we can ignore that. But our second term now, if we take the derivative with respect to q2, we're going to be left with a1, 1, 2, right? We're also, in the next line, going to have another one, k21, a sub 1. Note that these things are equal because they're k is symmetric, remember? So k12 is equal to k21. So we're going to have basically 2 of those, but then we have this 1/2 sign there. And so what happens is this moves to this other side, minus k21 a1. Now if you notice in this first line, The first term didn't have a Q, so that goes to 0. What about the other terms? Is there anything left in this first line that we would use when applying d pi dq2? No, because this is a sub 1 k13 q3. So the rest of these values are not included. So this term actually leads after applying we have a squared term of q2, but we also have this 1/2. So that's going to leave us with k22 q2. And that process continues all the way down. It does help to expand this and work it out, but you are left with, going through that process, you're left with something like this. So what it does is it allows you to move those values with applied displacements. They basically come over on this side. That's one artifact that you get. The other artifact you're left with are basically all your unknown values, Q2, Q3, etc., all the way to Qn, are still left on this side. So what we try to do is separate that out into matrix form. Our K's are known values, so we know our elemental values and our stiffnesses, so we can pull, all those are known. Our Q's are unknown, so these Q2, Q3 are unknown, and then this right-hand side is also known because the displacement A1 was given. So as a consequence, the finite element equations can be expressed in matrix form. So here's our K matrix, we know that. These are some of the things we don't know, and notice that we don't have a Q1 there, and also we don't have it here. So basically what we've done is we now observe that we have an n-1 stiffness matrix. And it's obtained simply by deleting or eliminating the first row and column, which is pretty amazing. Basically, if you took this global stiffness matrix before we had a K11 over here, right? K11 here. So there's another values. We basically just crossed out everything in that line. And it left us with what we call the reduced stiffness matrix. We can now represent this as KQ equals F. Sometimes I like to do K reduced when I write my notes to keep it clear that this is actually the reduced after I've applied the boundary conditions. This is obtained by eliminating the row and the column corresponding to the specified support degree of freedom. We can now solve this using Gaussian elimination, which you may remember from your linear algebra class. Note that reduced K matrix is non-singular, meaning that it does have an inverse. Okay, as long as the boundary conditions were specified properly. Interestingly enough, the original K matrix is a singular matrix. It does not necessarily have a guaranteed inverse. So this elimination approach, applying the boundary conditions, basically allows us to do this solution process. So once Q has been determined, you can calculate the element strain, right? B times Q, and then the stress, which is Young's modulus times strain. And here the Q, you have to extract the Q from the global displacement vector using the connectivity. We'll go through an example of that. But you can calculate displacements and stresses. Now, there is this thing called the reaction force, and those happen at the support. So in order to determine those, you have to go back. You can write basically the equilibrium equation for node 1. Where does that come from? A simple way I remember it is if you go and look at these equations, it's very similar to that, using basically the line that you eliminated, so the one that involves Q1. All right. So if you look at this, you have K11 Q1, K12 times Q2, and all the way over, and that equals to the force at 1. Where you have an additional reaction force that's unknown. This F could be an applied force. This is an applied force. So typically, if you're having an applied boundary condition, that's 0. What happens here is the Q2 through Qn were just solved for using the solution process. We know Q1 is given from our known conditions, so they're all known, and F1 equals the applied load. If there is any, it can also be 0, and consequently you can just solve for R. So you just do that, and you're left with a reaction force at the support. As we go through, we're going to get into the algorithmic procedures of this. We're actually going to go into MATLAB and do some examples, and we'll eventually compare it to Abacus. we have to store that in a different matrix. Okay, so the elements K11, K12 through K1n, which form the first row of K, need to be stored separately. So you have basically a global stiffness matrix, and I call it a K reduced. So you have actually two of those. Now in this case, we only looked at one boundary condition, but this procedure can be generalized to handle multiple boundary conditions, and we're going to look at that. So this is from the textbook, basically the algorithm. You consider the boundary conditions that go all the way to A sub r. You store those in the global stiffness matrix and the force vectors. Okay, you delete those rows and columns from the K matrix. You're left with a K reduced matrix, and then you solve for the displacement vector Q. Then for each element, you extract the element displacement vector Q from the large vector and determine the stresses. And then using the information stored in this step, you then compute the reaction forces all the way through for each displacement. So you can actually do that for each one, not just the support ones, but any node. Okay, so that's an introduction into the assembly process. We covered a lot of ground today, and basically we summed up the entire fine element program. So we can actually go from mesh discretization all the way to the solution process for the displacements at this stage. We've understood, we've seen the assembly process from going from the local to the global levels, and so we're ready to apply this. We're going to do an example and go through this assembly process, and we're going to build on it as we go. So I hope you've enjoyed this. I hope that you're starting to see how it all works, and I will see you next time.